Good evening, everyone. Hopefully you got through the weekend well. Kind of got a little colder, and we started getting some snow here. And it's a four-letter S word, so I suppose we can. But hopefully they don't get too mad at me for using it. But anyways, we had a little bit left in my grass this afternoon when I went out. But hopefully you guys don't have too much down there either. But we're in that time of the year where it's always tricky because the ground, as the ground freezes, it tends to turn. Before the ground is frozen, what will happen is any kind of snowfall and or rain that falls on the ground turns into ice, or has a possibility of turning into ice. So that's always a tricky part of the year until the ground freezes completely, and then the snow at least won't melt when it hits the ground. So this is a good thing. So we should look forward to the ground being frozen. Helps our roads at least. So today I want to talk about three different types of alternate or parallel processing approaches. So they're completely different than the von Neumann system that we've been studying, which is just pushing things down through. And we talked about some pipelining, some other parallel things, but these other three systems of computing they're kind of fundamentally different, and we'll explain how that all kind of works. So, we'll go through it. I'll go through it here. I should probably have a OneNote up. I don't even have that open yet. Geez. OneNote. File, new. Lecture 29. Press save. Oh, okay. T. And then put some space in there. That should give us enough room at least to start with. Okay. So the first one is called a data flow computing. Data flow computing. You redo that. See. So the idea behind data flow computing is that, in a von Neumann system, we're going to go through a decoding, and we go through different steps, where we're going to look at the data and make a determination on what's going to happen. In a data flow computer, that doesn't happen at all. It's just automatic. So what you have is different places where data can come in, and then you have other places where data goes out of the system. And there's potentially more than one input, and usually there's just one output, but there could be more than one output. Well, let me do a simple system. So let's say we have something that's going to solve trying to think. Say you've got you've got Pythagorean's theorem. So a squared plus b squared equals c squared. And you can rewrite this as c equal to the square root of a squared plus b squared. So what we can do is we can actually write this. So, okay, the way to think about this is there's inputs, which I'm going to put here like this, right? We've got an A and a B. And these get input into into a node. So we just talk about it like think about it as a thing that's sitting there waiting for data to come into it. And as soon as it actually gets data, then it'll assume its property. And then it'll output the result that it's looking to output. But what it does is it waits until all of its inputs have value, and at that point, then it'll send off its material. So in this case, if we give the two values for A and B, say that's 3 and 4. So then what happens in here, we're going to say this is going to be A squared. And since that's the only input, well, that looks a lot like A to the A squared. And this one is B squared. Okay, so what will happen is, because it only has one input, then it's going to go ahead and do that calculation, right? And so what it's going to do in this case is going to push the value 9. Now nothing changes about the computer when it does this node. The node just stays the same. Every time it gets data, it simply squares it and pushes it out the output. That's all it does. And the same thing for U, right? So we say that this is going to be a 4 here, and so it's going to square that, and that would be equal to 16 then. Okay, so then what we can do is, I know I drew these down straight, but let's go ahead and bring them in here, because we're going to have another situation. And what this is going to do is this is just going to add the two things together. So when it sees a 9 on one side and a 16 on the other, it's just going to add them together. And so we could say this is A squared plus B squared, or in this case, equal to 25. And then we have another node here. And so this one is just going to take the square root of the input. Input. So whatever comes in the input, right, it's just going to square root it. So then here we say A squared plus B squared under a square root, and in this case that equals 5. And this is our output out of the system. So realize that if 3 and 2 get pushed in at the exact same time, this is how this will work out. And so if I looked at it differently and I change this to a 4 and this to say a 5, then what we would do here is we'd have a 16, and here we would have a 25, and then when I added them together, I would get 41, and the square root of 41 is something like 6.5. 6.5 times 6.5 equals 42, so that's just a little bit high. So is there a square root function on here? There is. Okay, so let's go ahead and just clear this and say 41, boom. All right, so 6.4, we'll just round it off there. That'll be fine enough. At least for what we're doing here to get this idea. Right, so that would be a different number. But that's if the 4 and the 5 go in at the same time, because then these will work and then this works. And so what happens is we can take something that's much more complex as far as a mathematical formula. And for looking at these, that's generally what we're going to do. And so it takes that and it can just process it directly. Super, super useful. But only in specific situations. The book shows us how to do a loop with this. So let's say j equals some value of n, k equals 1, and then while j is strictly greater than 1, k equals k times j, and then j gets j minus 1. And then after that's all said and done, then we go ahead and return k. Okay, so let's look how this gets done in a Dataflow computer. The book has one way of representing it that I think just has too many lines in it, and I don't like it. So what I'm going to do is I'm going to show you something just a little bit easier. Because really, this just applies to one thing. All right, so let's assume here that we've got a node. And it has two inputs, a j and a k. And what this does, I'm going to go ahead and push that out to here. We should probably say if, so that this says j is greater than 1. We're going to choose that path. If it's not, we're going to output this direction. So this will be our output. That would be j less than or equal to 0. We're forcing j and k both to be integers. Okay. So I don't need this if here, it's just a decision. Okay, so then down here, so this is the condition in order to go this direction, but what are the values of j and k? So because we're going to do some work, right? So we're going to say j equals, although we wouldn't do it this way, it equals, well, let's go back to our algorithm here, j equals j minus 1. J minus 1. And k equals k times j. All right, so, okay, and then down here, what we're going to do is we're going to do this, like this, and we'll say if j is greater than 1, do this. J equals j minus 1, and k equals k times j. And then I'll have another one here that'll say j, oops, should be less than or equal to 0. And I should probably put on these, so then this one would be just simply k, and this one would be just simply k. as well. So we think about this when it comes into this node. There's both of these nodes are doing the exact same thing actually, and that is it's going to check that value. If this is no longer true anymore, it's just going to go ahead and go straight to the output. All right. So let's assume, let's say n is, let's go 5. It's a little simpler. And then k is equal to 1. So then we come down here and j is not less than 1. So then we would say this is 4 here, and this is 1 times 4, that's 5. Okay. So then in here, we're going to check, and it's going to say, well, j is still greater than 1. So then we're going to say j is equal to 3 this time, and k is equal to these two multiplied together, 20. All right, now switch to the next color, because these can't come in, and then it looks at those and says, well, no, that's not big enough, and so then it's going to multiply, and we're going to get 60 here. Go to the next one, get a 1, and then what, 1,200. Now, when this stuff comes in, we see that, oh, wait a second, j is not greater than 1. It's actually equal to 1. And so we're going to go ahead and spit out this direction, and we say this is equal to 120, and that would be what was on the line. So the 120 would be output, and that'd be the end of it. So what it does is it lets things move through this machine, as it were. And this looks a lot like something called a Turing machine, which I'm guessing most of you aren't familiar with. Really super fascinating way to do things, and that's what the model is for this one. The cool part is we can do all of this right in the circuitry, and because it's not waiting. In this case, we've kind of added a little bit more to it on how it decides. We would probably have to break it out similar to the way the book does it in order to get a better understanding. The problem is there's two variables floating around in there, so it's a little harder to understand. That's the reason why I don't like the book one. But if the two inputs are there, we're going to go ahead and fire and start up our machine. And so right at first, this is blank. It doesn't have anything coming down that line, so then this doesn't do anything. It just sits there waiting. And then, that actually, in some ways, it becomes a problem because, see, this won't fire ever again. So then we have to look at one or the other, not both. In this case, this one required both. This one only requires one or the other. So that would be a little bit difference on that. And that's the reason why I didn't loop this back into itself, because it's a little harder to know when it should fire. Okay. That's the idea of a data flow computer. The next one, and I think by far the neatest one, is the neural network. And I'm sure you've probably heard this before. Neural network. That just sounds complicated. Well, and it is. So that they're not wrong. So this is the exact same idea, right? That there's these nodes, or in this case, they're actually formally called processing elements. Now these are specialized, though. So I'm going to draw a thing here, but these are specialized. So let me explain how they work, at least a little bit. So what a processing element does is it takes in one or more inputs. Actually, it needs to be more than one. It takes in several inputs, so it could be two or more, and then it uses those to inform let me back up. It assigns a weight to each of the inputs. And by doing this, it So it gives each one more priority or less priority based on the weight. So the higher the weight, the better. So, and all of the weights are between 0 and 1. So then it uses that information, does some mathematics, and decides on its own output. And usually, okay, let me give you an example here. Let's say I have a picture. And we're to talk about image recognition. Let's say it's a facial recognition, right? We've got the smiling student because they're doing really well in class. So what happens is we're going to look at every single pixel in here, every single one, all of them. So let's assume, let's just say there's, just for ease of math, 30 pixels this way and 30 pixels this way. Oops, not 39, 30. 30. So that would be 900 total pixels, 900 pixels. That all have an input coming in to them, into our network, okay? So there's 900 of them. And then usually this is going to have 2 layers. And this could have a number of them. I don't know how many it is. I should put some dots in there because I just don't know. And then there's another one, and this second one here is going to have the exact same size. Okay, now, oh, and this, all of these go here to our output. And this is our output. Okay, so let's assume that what this is doing is it's trying to decide if this is a picture of a face. So each of these data points contributes to several different ones here, and each of those has a weight. So like say 0.8, and this one would be say 0.3. It doesn't matter at all what's going, so this might be 0.4. So they don't necessarily have to add up to 1 or any of that kind of stuff. Just that's the weight. And so it's going to multiply that by the value of that's on that system. And then that's going to tell us, it's going to help us inform. And then these are all connected here as well. And so, and these also all have weight. Say 0.7, and this has a weight, say 0.9. Etc., etc. Okay, so, but the value that comes, so that, okay, at the end, this is an output of 1 or 0. Here's the part in neural networks, because it's actually, it doesn't know how to do it to begin with. And so all of the weights could be arbitrary. It could just pick a number, it doesn't matter. As long as we have the connections correct, we're good. So then what happens is, if we're looking for a face, and say this pixel is up here in the corner, does that one matter? Probably not. But our neural network has to learn this. So what we need to do is we feed it a bunch of pictures of faces, and we tell it, this is a face, this is not a face. This is a face. This is not a face. And so it's going to go ahead and go through the different pictures. And so what it's going to try to do is for the pictures that are a face, when it's supposed to be a face, then the values here. Oh, okay. Let me back up. because each of these nodes either fires a 1 or a 0. All of them. But these actually are bringing in actual values. So it's going to fire a 1 or a 0. So that, say that 1 goes along here, and then that weight helps provide this some information about that pixel. So if this pixel is on, has a value of 1, let's say, and that's a light or whatever, then that informs this node. And so if it's decided that this is actually a face, then it says, okay, well, if this is a certain color, that actually, maybe that's what means that this is a face. Now, it turns out that that's not correct anymore, but the neural network can make that assumption. It doesn't do it in the same technical way that you and I think when we look at something. But what it can do is, as it gets results of whether or not this was a face, it slowly learns and can change the weight in the system. Each time, each iteration that it gets one right, it can change that weight just a little bit more until it's done learning. Also, when it gets one that's incorrect, right? So if that's not a face, that gives it a little bit more information as well. And so each time it's able to kind of work on those wait times, not wait times, but sorry, the weight values. And so now here's the interesting part. If we had to look at, say, this one pixel here, how many possible relationships are there between this pixel and the other pixels on the board? Well, 899 of them. That's a lot. In this case, we're going to push in the 900, and then we're going to drop down to, say, maybe 16 different intermediate values, and then those will affect a subset of the 16 in the next group, and that'll affect 1. So it boils down all those comparisons to smaller number of comparisons. Because here we have 16 times 16, which is a much smaller number. What is that, 1024? No, it's higher than that. 2024. Okay, I think 2028. Calculator. 64 times 64 equals, 4,096. That's different possible links between these two groups, but they're not all necessarily present. So there's that as well. So that's what a neural network does. But here's the thing that when we look about this practically, that's extremely important, is this neural network is only as good. Well, first off, what affects how good it is how the nodes are connected, how these processing elements are connected. But the other thing that's super important is what kind of learning algorithm we use with it. When we say we're learning algorithm, we're talking about what kind of a process to learn that it's going to use to learn. Because this can throughput things, it can make decisions much, much faster once it's set up and working. Because, right, we can feed all of those in at the same time. It clicks through that, and so this will just take, 3 cycles. As long as we've got those weights figured out. Now, there's problems with this. Because if your learning algorithm or your learning set or your pictures, in this case, that you're using to try to do facial recognition, aren't nuanced enough, then you'll receive a bad result. So there's a historical example for this, actually, as it applies to facial recognition, is that when they first did facial recognition, they, well, and rightly so, right? They said, okay, well, what's the easiest way to fool in a picture? What's the easiest way? Well, it would be to try to find something that's a picture of something that exists that looks like a human but isn't. So they came up with, well, the thing that they thought about was, I believe it's orangutans, right? But it's one of the apes. So they use that because it's the closest known relative, or it looks the most similar to humans. Okay, so, and the neural network gets this. And then they fed it a bunch of pictures of humans and said, here, these are pictures of humans, these are pictures of non-humans. And the neural network was able to go through and actually make all those. I don't know if it was a neural network, but it was able to go through and figure it out, kind of get the weights figured out and realized what was and wasn't a picture. And it was very good about deciding whether somebody was a person or not when it looked at a picture. It could figure it out, with one exception. Anyone with very dark complexion, it would think was a non-human. This was not intended. Not in the least. And it wasn't necessarily an oversight with the group necessarily, because the neural network just simply said, it made the determination that the pigment of your skin helped determine whether you were a human or not. Now, the humans that were doing this didn't know that that's what was going on, right? Because they're not looking under the hood. It's just too complex. There's no way you could possibly do that. And so, but the results were there. And so many of the early facial recognition software did not do a very good job for people with very dark skin. Now, my hope is that that's been corrected. I don't know for sure that it has, but it certainly is something that needs to be fixed. And the same could, the same could have happened in lots of other different ways. And part of it might just have been that they didn't have good enough test data. But that's a cautionary thing, right? You want to make sure that you have enough test data to get it so that it correctly recognizes. Because the whole idea, the reason it's called a neural network is it's designed to work like the human brain. And the problem is we don't really completely understand how the human brain works. So we can't perfectly model it. So they tried their best, and they got it wrong. And they went back to the drawing board with the tail between their legs and tried to correct it, I'm sure. So there's that. Okay. It is also possible for a neural network. Another example of a neural network, this is where AI starts coming in, is that we could teach a neural network all the different possible moves that it could make on a chessboard, just as an example. And then it will play a bunch of games of chess. And so it'll make its moves as it goes. But what happens is, at the end, it remembers all of the moves it makes and all of the moves its opponent made, and then it knows who won or lost at the end. And if you win, the weights go up for the moves that you've made. If you lose, all of the moves that you have, the weight goes down. So it's less likely to pick that outcome again. That particular move. So what ends up happening is it doesn't necessarily know what the right move is, but it says this move was used in a successful win. So I'm going to assume, or I'm going to have some indication that that's something I should value. That move there was a move that helped me get to a winning state. And it does the same thing with the losing states, or losing situations. And so it can slowly build up and get better and better and better. In fact, if it's fairly well designed to begin with, the neural network can get, so let's say it's a AI for a computer opponent in a game, it can get so good that you can't beat it, especially if you used you to train on, because it knows how you play the game, and it will know, it will be able to predict what the best move is to defeat you. Not any player, but any specific player, but the player it trained on. So that's that's another thing that's out there. I don't think any AI computers do this. They're actually dumbed down on purpose. It's possible that they're not. Okay, next one. Systolic arrays. So normally what we think about for a systolic array is we have input that comes in here, and then it just goes through all of these processing units in the array, until it gets to the end, and then it outputs that value. And that's a good way to think about it, is it's just going to, and there's no decisions to be made, it's just going to chug right along. This is useful because this kind of sets up a pipelining thing as well, right? We can kind of, you know, run things along here, so that one thing is in this state, and the next thing is here, and the next thing is here, and the next thing is here, and then each clock tick we're going to move forward one, and it's going to do whatever it's supposed to do, and it's going to output its value, and then this one receives it. And so, right, we can see kind of pipelining at that point. So the other thing we can do is it actually is really useful for doing matrix mathematics. So when you take two matrices, and so let's just assume, let's say they're both 8 and 9. They're both 3 by 3. Now, to distinguish them, I'm going to number this one the opposite direction. Not that it really matters. Okay, so we have a value here. Well, and that value is these 3 times these 3 added together. So 1 plus 2 times 2, 4, plus 3 times 3, 9. So I get a 14 there. Each one of these other ones has 3 parts that it has to do multiplications for, and then adding them all together. So the multiplication would be 3 times 9, or 27. Okay, but it's not that simple, right? Because I have to fetch each one from memory and do all that kind of stuff. Okay, but instead, let's create this 1, 2, 3. And I'm just going to do this. So I'm going to create this grid here. All right, and then I'm going to do this 1, 2, 3 here. Okay, so I'm going to push this in so that this 3 is in here, and this 3 is in here. So I just take those two and multiply them together. And then this 3 goes on to there, and this 3 goes down. And as I do that, I push the 2 in there and the other one in there. Now, over here, this one is 4, 5, and then multiply by 6. And this one is 4, 5, and this one will be multiplied by 6. So I get an 18 here and an 18 here. Now the values don't really matter that much, but then the next thing I do is this 6 goes down here. I replace it with a 5. But that 3 doesn't stay there. That 3 and this 2 slide over, so we get a 1, a 2, and a 3. And then we can erase this one here, and then we need to move this down. Yep, we already did that. So then over here we have a 7, an 8, and a 9. Oh, and this is gone now because that went into there, 1. But then this should get a 2, and this gets a 3, and then I'm gonna by 6, and this times by 5. And then down here I have a 9 that goes in there, and a 7, and an 8 here waiting to go in. And so, oh, I didn't do this, the addition here. It was, oh, it should be a 1 now. It was 2 times 2, right? 2 times 2 is 4. And then here I'm going to get this 1. And so then this one will be, right, plus 10. And then it'll be 4 times 1, so plus 4. 10, 20, 32. And this one would be, what, 27 plus 16 plus 7 would be 34.50. Is that right? 14, 20, 30, 40, 50. Yep. Okay. So, and there's some symmetry in the way this all works out, but we don't have to worry about that. But notice here, these just slid right by each other. And so, in some ways, that's kind of how it works in this situation as well, is that we can do them all at the same time. And so it helps with parallelization, because it allows us to kind of know how things are going to work out. So matrix multiplication, by the way, is very, very important because it's used in graphics. When you're doing, actually not even that high end of graphics, you do have to do matrix multiplication, to multiply multiple matrices together, and the systolic arrays do a really good job of that very, very quickly. Whereas a regular computer, regular inline, might take, hundreds. Right? What did we figure out? And it was 9 times 3 is 27 different comparisons it needs to do, multiplications. But because this does this in serial, it will be, in this case, I think it's 4. No, it's not 4. It's like 7 or 8. I had to do them all to make sure that, because each one is going to be delayed. Well, this is delayed by 2, and then it has 3 clicks it has to go through, so that's only 5. So it still does all the multiplication, but it does it simultaneously. So that's the difference in some ways. Okay. So then the very last thing I want to talk about is quantum computing. So this is tied to quantum physics. My guess is few, if any of you, have done any studying in quantum physics. Here's the thing that's interesting. So quantum computing, okay, wait, let me back up. It's the idea of computing. So quantum physics is the physics that's lower than an atom. So it's looking at electrons, it's looking at protons, it's looking at neutrons. And things that are even smaller than that. Quantum computing makes use of these electrons or protons or neutrons for computing purposes. It actually has to do with how the electrons are spun, and there's a lot of different tricks, a lot of different things to it. But, so in a regular computer, we have a bit, just a regular bit. And so if we have a bit, it's either 1 or 0. So in quantum computing, we have something called a qubit. And a qubit is not strictly 1 or 0, although you can force them to be that. It's because each one has a probability attached to it. So we could say it's a 0.61 and a 0.40. So 60% of the time it's a 1, 40% of the time it's a 0. So we could call that definitively, we could say that's a weak 1, but it's at least a 1. When you have 2 bits, how many different possibilities are there? Wait, let me back up. If you have 2 bits, right, yeah, if you have 2 bits and look at the different possibilities, right, you have this, you have this, you have this, and you have this. So I can just simply write it down, no problem. Now, in a qubit, if I have 2 qubits, it's not that simple. Because you see, I need both of these 2 pieces of information. I'm sorry, not that one. I need both of these 2 pieces of information. So, right, I could write A and B. A and B. And then if I had a second qubit that had those same values, I would have to have a C and a D. I could draw that the other direction, I guess. That would make it a little easier. So in this case, I have an A, a B, a C, and a D. Oh, I didn't talk about this. So one of the things that makes quantum computing really interesting is that these qubits, they become what's called entangled together, meaning they affect each other. So when they're independent, that's what they are, is independent. But when you bring them together to try to solve something, they will affect each other. They'll change each other. Which means that it's not just a simple mathematics problem. It's much deeper than that. But in order to figure out, this out on 2, right, you need to do this. Now, this expands with a 3rd qubit to 8. Let me explain. Because here, right, I could just do 0, 0, 0, 0, and then I could change. Actually, it'd be better if I put the zeros on the other side. Be more like to what I'm normally used to seeing, right? And then I could do, and then 0, 0, 0, 1, 1, 0, and 1, 1, which gives us 8 different solutions. But it's only 3 bits. The problem is here, this has to give a probability. So, okay, wait. that's where it gets cool. Okay. So let me draw this differently. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. So when we have this, each one of these is a probability. So the first one is a probability that that will happen. And then probability that this will be the case. And then a probability that that'll be the case. And another probability that this will be the case. Because it's not always the same probability that the first bit or the qubit will be a 0 or 1 based on it's not the same for all things, right? So when this is a 0, this has a distinct possibility to be a 0 based on the entanglement between them. So, but when this one doubles, right, it goes to 8, then we have an A, a B, a C, a D, an E, an F, a G, and an H. So you'll notice here that in a regular bit, every time you add one, you double the different number of possibilities. For a qubit, we're doubling, but it's, so this says, okay, for every bit we have to add, we're going to add a single bit to the output to be able to figure out, to be able to write it down discretely. With qubits, every time you add one, instead of adding one bit, you have to double the size of what's the output already. So what can happen is, let's say you only have, say, 30 qubits. But then the number of possible outcomes is, it turns out to be this, 2 to the 30th. Well, 2 to the 30th is some number around 1 billion. That's just a rough number. It's going to be higher than that, but that gives us a magnitude about how much it is, right? That's roughly 1 billion. But that that's right. That's 30 bits, 30 qubits. If we just had 30 bits, it would be 1 billion possibility, but we would only have 30 digits. If we're using qubits or quantum computing, this is 2 to the 30th, or about 1 billion qubits. Not characters, letters to describe values, to describe that relationship. Digits. We could read that as values as well. So this is where quantum computing comes in. There's a couple other things with quantum computing that are quite interesting. Every time you measure it, it changes the state of a qubit. So it's no longer the way it was when you measured it. It becomes a problem, so we can't test it, not properly. So now I couldn't tell you how useful it's going to be. People have been working on this for well over 50 years. They do continue to make progress on it. I've heard in the past that it's 5 years from market. I've heard in the past that it's never going to go in. I don't know what the consensus is. I couldn't tell you. All I know is this is the idea of qubits. Now, there's way more to it, and you'd probably have to understand. You'd have to understand quantum physics in order to really understand it here. The other thing that's important to note, and I should have talked about this kind of at the beginning, each one of these qubits, as it's not capturing a value, it's actually capturing a wave. So it's some kind of an amplitude wave that gives you an idea of which is possible and which isn't. And that's important to note, is that you're trying to capture a wave, and that's why it's really difficult to do, right? You can capture it at one point in time, but you don't know what that's going to be in the future, and especially since you know that when you do measure it, that actually corrupts it. So they're still working on these things and trying to figure it out, but that's the way it is. So and a little bit about quantum computing. Now I have waved my hand a lot, I'm sure, and it's not very solid on any of these, to be fair, but this is just a real basic rudimentary knowledge of them. If you want to find out anything more, there are wonderful both videos and websites, and that will help you learn way more about these four things than you know now. And I think knowing more about them can be very helpful, especially since they do each one of them, when it comes to programming, requires a different way of thinking about the problem. And again, that's kind of, in some ways, that's the whole point of this whole course, is to teach us different ways of thinking about problems that will then help us in the future as we're looking at problems. And so that's an important note. All right, I put up assignment 8 today, and that covers both chapters 7 and 8. Next week we'll have one on chapter 9, and then I'll see about getting a programming assignment up by next week as well, so that you guys will have that some assembly language code to work on. All right, that's all I have, and I'm going to cut it a little short today because there just isn't that much material. So we'll start looking at embedded systems next time. And does that include one of my favorite topics, which is RFID? Probably not, but certainly RFID would be I'm not seeing it in here. At least it doesn't talk about it. That doesn't mean it isn't in there somewhere. Right, RFID are those little circuits. You can kind of see them. You can see the metal in them, but they look like a sticker most of the time. And then they'll put them on products, or those things that they put on clothing that they have to take off when you buy it. That has something similar to RFID in it. So they're super cool. They're super cool because it's a little computer that is powered by the radio wave that it receives. And it allows it to do a small amount of computation and to reply back, but only at very short ranges. I'm talking like 5 to 10 feet. But the cool thing is they actually make stores that not make them, well, they made them, but you could have a store where everything in the store has an RFID tag on it. That tag itself can communicate where it is. So when you put the item in the cart and start moving around the store, there's like maybe a tablet that's attached to the cart that knows what you put into the cart, and it tells you what the price is, and maybe even makes some suggestions on other things potentially, right, that you might want to get with it. So that way you could know, hey, what's in my cart? Just like similar to your online experience, right? But you don't have to scan it in or anything. You just put it in the cart. And then when you get ready to leave, you've already put your credit card information into this tablet. You've scanned it, so you get to the door, you just go out the door and walk out to your car. You don't have to check out because it's all right there in that computer. It deducts it. As soon as you go through the doors, it recognizes the card is through the door, and done. So it allows you in a shopping situation to focus on shopping. And I think most people like that. Most people would like that. It means you don't have to stand in line when it comes time to leave. You don't have to worry about people going through all your stuff to see what you bought, like they do at some places, right? They'll make sure that you, oh yeah, you bought that item, yep, you bought that item, yep, you bought that item. Well, but the computer just takes care of everything for you. So, all right, that's all I've got for today. I will talk to you all in a couple days, and we'll do some first parts on the embedded systems. Well, let me look. Actually, maybe I'll start Marie next time. Actually, I think I should start Marie next time. So I'm going to switch up a little bit, and so we're going to do some Marie next time, and I'll do how to set it up, so that way you guys can get, and then see if I can come up with a program for you to do, so that way you can get a chance to get after that. So, okay, sounds good. I will talk to you all again in a few days. All right, bye-bye. I will talk to you all again in a few days. All right, bye-bye.